Hey everyone, and welcome. Today we are diving deep into a real classic, WordBreak 2. This one's famous, or maybe infamous, for popping up in some of the toughest coding interviews out there. But don't worry, it's a fantastic problem for really understanding some powerful programming patterns. So, let's crack it together.
Okay, here's our game plan for breaking this thing down. First, we'll get a solid grip on the challenge itself. Then, I'm going to show you a really slick, two-phase strategy that makes this whole thing manageable. We'll look at each part, what I call the scout and the builder, and then we'll wrap it all up with the performance stuff and the key ideas you'll want to remember.
All right, first things first, the challenge. Before we can even think about writing code, we have to make sure we're all on the same page about what we're being asked to do.
So the setup is pretty simple. We get two things. First, a string with no spaces, like cats and dog. And second, we get a dictionary, which is just a list of valid words we're allowed to use.
And here's the mission. Our job is to find all the possible ways to put spaces into that string so that it forms a valid sentence. And by valid, I mean every single word in the sentence has to be in our dictionary. So for this example, you can see there are two ways to do it: cats and dog, and cats and dog. Our program needs to find both of those.
Now you might be thinking, why don't I just try every possible way to split the string? And you could, but that would be way too slow. It would definitely time out. So we're going to use a much smarter approach. It's a two-phase strategy that I like to call the scout and the builder.
Think of it like this. First, we send out the scout. The scout's job, using dynamic programming, is to run ahead and just check for feasibility. It answers a simple yes or no question. Can we even make a valid sentence from this point forward? It doesn't build anything, it just marks the viable paths. Then, once the scout has mapped everything out, we send in the builder. The builder, using depth-first search, follows those good paths and actually constructs all the solutions. This way, we don't waste any time exploring dead ends.
Okay, let's dive into phase one. Let's see exactly how our scout uses dynamic programming to map out the terrain. We're going to use a pretty simple tool, a Boolean array, that we'll just call DP. Now here's the really important part to understand. When we say DP at index I is true, it doesn't just mean something about the character at I. It means that the entire rest of the string, from that point all the way to the end, can be broken down into valid words. It's a look-ahead check. So where do we start? Well, we kind of give ourselves a little freebie. We set the value for the position after the very end of the string to true. You might wonder why. Well, that position represents an empty string, and an empty string is, by definition, a valid segmentation. This gives our logic a starting point, a known good spot to build from. Okay, here's how the scout actually works, and it's a little counterintuitive. We work backwards from the end of the string. At every single position, we try every word from our dictionary. If we find a word that fits, we ask the million-dollar question. Does placing this word here connect me to a spot that I already know is solvable? And we know that by just checking our DP array. If the answer is yes, then bam, we mark our current spot as solvable too.
So after the scout has done all its work, what do we have? Well, our DP array isn't just a list of trues and falses anymore. It's a map. It's basically a treasure map left by the scout telling our builder exactly which starting points are promising and which ones are total dead ends.
All right, map in hand, it is time for phase two. Let's bring in the builder. Its job is to walk those paths that the scout marked and actually put together all the valid sentences.
For this phase, we're going to use a recursive function. You'll usually see this called DFS, for depth-first search. And its job is really clear. You give it an index I, and it promises to return a complete list of every single valid sentence that can be built from that point to the end of the string.
And this right here, this is the absolute key to the whole algorithm's efficiency. Our builder is smart. It doesn't just try random stuff. Before it even considers placing a word, it checks the scout's map, our DP array. It only moves forward if the word fits and the scout has already confirmed that the rest of the path is good to go. This one check saves us an incredible amount of wasted effort.
So what happens when the builder finds a valid word to place? It calls itself. It's recursion. It basically says, okay, I've got this first word handled. Now I need you, my recursive helper, to go and figure out all the possible ways to finish the sentence from where my word ends.
And then, when that recursive call is done and comes back with a list of all the possible tail-end sentences, the job is easy. Our current function just takes the word it found, adds a space, and sticks it onto the front of every single one of those tails. That's how we assemble the full solutions, piece by piece.
But we can make our builder even faster. We give it a memory. This trick is called memoization. We use a hash map, which is like a little notepad.
If we ever ask the builder to solve for a piece of the string it's already solved before, it doesn't do all the work again. Nope, it just looks up the answer in its notepad and gives it back instantly. This avoids recalculating the same stuff over and over.
And that is the entire process. The Scout checks with DP, the builder constructs with DFS. So let's wrap this up by talking about performance, and the one big idea you should really take away from all this.
Now, you might see the words exponential time complexity and get a little worried. But here's the thing. In this case, that's actually okay. The problem is asking us to find all possible solutions, and sometimes there just happen to be an exponential number of them. Our algorithm is efficient in that it doesn't do any extra work to find them. The same goes for space. We need enough space to hold all the answers we find.
If you remember just one thing from this whole explainer, please make it this sentence. This is the entire philosophy of the solution, summed up perfectly. Dynamic programming scouts the territory to tell you where you can build. Depth-first search is the builder that figures out how to build it. And memoization is the efficiency trick that makes sure you never build the same thing twice.
This scout then build pattern is incredibly powerful, and it shows up in a lot more places than just this problem. So my final question to you is, where else could you use this? First, checking if a solution is even possible before you commit to building it. Keep that pattern in your problem-solving toolkit. Trust me, it's a real